Welcome to our lesson on scaling load balancers. In today's interconnected world, applications need to handle immense traffic, and load balancers are at the heart of distributing that load efficiently. But what happens when the very component designed to prevent bottlenecks becomes one? That's what we're here to explore. By the end of this session, you will be able to first, identify common load balancer bottlenecks in high traffic systems. Second, compare different load balancing strategies, understanding their trade-offs. Third, explain the powerful L4 and L7 hierarchical splitting pattern used by hyperscalers. And finally, apply these concepts to design more resilient and scalable architectures. Let's dive in and transform potential bottlenecks into battle-ready systems. Imagine your amazing AI agent service hits 50 million daily requests. You're celebrating, right? Not if your monitoring dashboard shows a terrifying flatline. Not due to downtime, but because your single powerful load balancer is maxed out at 100% CPU. Every request suddenly takes 200 milliseconds longer. This is the hidden single point of failure that can bring down even the most successful systems. You see, when you scale horizontally by adding more application servers but keep a single load balancer, you haven't solved the problem, you've just moved the bottleneck up one layer. A major cloud provider experienced a widespread outage in 2020 not due to their edge servers but a configuration issue in their load balancing layer. This highlights how critical it is to anticipate and plan for this bottleneck before it impacts your users and your business. Let's look at some fundamental strategies to tackle this. First, we have DNS round robin, often called the budget superpower. It distributes traffic by simply returning different IP addresses for the same domain name. It's elegantly simple. No single load balancer sees all traffic, and you can add capacity by spinning up more load balancers and updating DNS records. The catch? DNS caching. A user's browser might cache an IP for hours, meaning if that load balancer dies, the user experiences downtime until their cache expires. Next, we have high availability pairs. This involves two load balancers, one active and one passive, sharing a virtual IP. They communicate via heartbeat packets. If the active node fails, the passive node takes over almost invisibly. Active-active HA is more sophisticated, with both nodes handling traffic simultaneously. While this maximizes resource utilization, both DNS round-robin and HA pairs have limitations. Either a lack of intelligence or being constrained by the capacity of just one or two nodes. When you're operating at internet scale, you need a more powerful approach. L4 and L7 hierarchical splitting. This is how hyperscalers think. Layer 4 load balancers operate at the TCP or UDP level. They're incredibly fast, handling millions of concurrent connections, but they're dumb. They just forward packets based on IP and port with minimal CPU overhead. Layer 7 load balancers, on the other hand, are intelligent. They operate at the HTTP level and can route based on URL paths, headers, and even cookies. This intelligence comes at a cost. They are much more CPU intensive. The pattern is this. Deploy a small fleet of ultra-fast L4 load balancers as the first tier. These L4 balancers then distribute traffic to a larger pool of L7 balancers, which then intelligently route to your application servers. A major streaming service uses this exact pattern, with their L4 layer handling raw packet forwarding for hundreds of millions of connections, distributing to L7 instances that manage intelligent routing, authentication, and dynamic traffic shaping. This combines raw throughput with smart traffic management. We've covered a lot today. Let's quickly review the core strategies for scaling your load balancer layer. First, DNS round robin provides cost-effective distribution, but remember its caching caveats. Second, high availability pairs are excellent for ensuring uptime, though they have limitations for massive horizontal scaling beyond 2 nodes. And finally, the L4 plus L7 hierarchical splitting strategy offers the ultimate combination of scalability and intelligent routing, essential for hyperscale systems. The real lesson here is critical. Your load balancer will become the bottleneck. Plan for it, design for it, and implement these strategies before that 3 a.m. pager goes off. Now for a quick self-assessment. Which load balancing strategy would you choose for a new service expecting rapid, unpredictable growth, and why?